everyone, and welcome back to the Regeneron Science Talent Search Public Exhibition. It's Christine Yee again, your last year winner, returning with another group of talented finalists. Let's dive right into the wonderful world of math. First up, a question for Thaddeus. Thaddeus used machine learning to detect and characterize quasi-periodic oscillations, or QPOs. First of all, what are QPOs? And second, how does your model help us better understand them?
So thanks for the question. QPOs are flickering in the light around black holes that are about the mass of the sun, and it's emanating from not the black hole itself, but the accretion disk around them. And to the second question, my model provides a framework, an architecture, and an approach for looking at these from a different angle than what's been traditionally done in the past.
Amazing. And now we have Sally. Tell us about your work to better understand waves' internal lives and how this might help scientists in fluid dynamics and oceanography.
Thank you for the question. So in my project, I studied internal waves, which are like ocean waves, and you can imagine that you have this fish tank with water in it, and after some perturbations, according to a given wave equation, the water will begin to move and form some pattern. So I looked at a specific pattern that these waves could form. And studying internal waves is relevant to oceanography because these models and these equations can act as good two-dimensional predictors of ocean waves and as predictors of their long-term behavior.
Awesome. Next up we have August. August, I know we are all impacted by your research, which focuses on the algorithm behind multiple technologies, including popular voice assistants. What did you modify, and how does that help improve people's privacy while using these tools?
Right, so I helped modify, so federated learning would allow machine learning to learn from data while keeping that data private. But part of the reason why it's not being used right now is because one of the steps is very, very slow and inefficient. So I found a different way of doing that step that is more efficient and runs faster, so it does not slow this process down as much, and it is much more feasible for real life application while still keeping the data private.
That's awesome. Okay, next we have Linda. Linda, you studied exoplanetary systems and how they change with encounters with primordial black holes. What is the relationship between these two amazing space objects?
So exoplanets are just planets outside of our solar system, and primordial black holes are a specific type of black holes that are hypothetically existing in the universe. So I looked at how close encounters between these two can shape the orbits of the exoplanets. So I essentially predicted the exoplanet orbit distribution of exoplanets by looking at their close encounters with primordial black holes.
Awesome. Okay, next we have Max. Big question, what is S-calculus and what are some of its applications?
So S-calculus is a generalization of Q-calculus. So first, what's a generalization? Well, in math, it means you're extending a definition or theorem so that it works in more cases. Second, what's Q-calculus? Well, it's another version of calculus that's kind of more discrete. It doesn't use limits at all. And a lot of the theorems of calculus still work for Q-calculus as long as you modify them a little bit. So I proved theorems in S-calculus, which still work for the S derivative, but had to be modified. That's basically what I did. Oh yeah, for applications, I don't know yet because it's pure math, but I mean, there's a chance it has applications in quantum physics because Q-calculus does.
Awesome. And then keeping things in the abstract, Sophie, what question did you study in your project and what drew you to it?
So in middle school and high school, we learned that the integers have unique prime factorization, which means that every single integer can be written uniquely as the product of prime numbers. So when we get the sets a little more complicated than the integers, prime factorization may no longer be unique. So essentially in my project, I studied when factorization exists and is unique in a specific type of set called Laurent evaluation monoids. And I started this project because I'd always been involved in number theory and I really enjoyed it, so I applied to this research program that assigned me to a mentor in the area.
Awesome. Okay, turning to Ethan. Tell us about online learning and your work in data forecasting.
Alright, so online learning is not the same as like virtual learning. It's a branch of machine learning in which maybe instead of getting a big batch of data all at once, you kind of get data continuously, which is both for training and for testing. And so my project's about the online learning of functions, which are just quantities that you can track that depend on certain inputs. And so how this applies to data forecasting is if you can kind of capture how well you can learn some classes of functions, this can help you refine your models for processes that evolve over time, such as the weather or stocks.
Great. Now, Michelle, tell us about the algorithm you created and its real-world applications.
So in my research project, my algorithm basically uses deep learning to reconstruct a 3D human model from a 2D image, such as one taken from our cell phones or tablets. And how it does this is through a convolutional neural network and regressor to non-linearly regress features and parameters to reconstruct the model. And some real-world applications include like virtual reality, augmented reality, and 3D broadcasting. For example, on the Olympics, you can broadcast athletes' performances into 3D so that viewers can see it from all different angles.
Awesome. Now, Evan, tell us about high-temperature superconductors and why they are important.
Yeah, so superconductors in general are these materials that are able to conduct electricity without resistance. And they all have a transition temperature where they go from being a normal material to a superconducting material. And high temperature superconductors in particular are the ones that have a transition temperature that's pretty high, and so it's easier to get them to the superconducting state. And they're important because they can be used in all sorts of applications, from like maglev trains to just plain superconducting wires, which are lossless.
Awesome. And then finally, Madeline, tell us about mathematical knots and how you got interested in them.
Right, so mathematical knots are these 3D objects. They're closed curves in space that don't intersect at themselves. So essentially the way you could think of that is by taking a piece of string, tying it up, and then closing the ends, and that would give you a knot. I got interested in knots, and especially in this particular knot mosaic invariant, just because there's still so much we don't know about them. This invariant, we don't totally know how to compute it yet. We don't really know how it interacts with other knot invariants, so I was really interested in pursuing that question.
Amazing. Everyone, thank you for talking to us about your amazing work. We've got another group of students to talk to, and you definitely want to stick around for the next one. In the meantime, you can check out our other finalists' work on the Public Exhibitions webpage, which is linked in the Society for Sciences bio. Thank you.